the airport in Paro, which was fantastic. We kind of landed through the valley. It was a spectacular sight, and we look forward to kind of spending a few more days here, seeing Bhutan, which would be really exciting. Throughout the last 20 years, I've actually been working on earthquakes in the Himalayas. I've traveled to different parts of the Himalayas, except Bhutan. So this is a grand opportunity for me to see the Himalayas, which I hadn't visited. So what I'm going to talk about today is to introduce you to what we have learned over the years about the Himalayas and Himalayan earthquakes, and why we as a society should be worried about it. So if you were to talk about preparing for disaster or dealing with hazards, step one would be to understand the science. And I'm going to give you a glimpse of that through my presentation. It's about 30 minutes, but no one, please feel free if I run over my time to stop me and I'll conclude. This is a broad outline of what I'm going to say. First is I'm going to convince you as to why as a society we need to worry about earthquakes. I don't need to convince you, actually all of you most probably have felt an earthquake, you understand the seriousness of earthquakes. But still I'll kind of quickly take you through that. Once I do that, then I'll give you the broader picture as to why you have earthquakes. So I'll take a step backward, talk about plate tectonics, and from that I'll lead you to earthquakes. The consequence of earthquakes are basically faulting. Then I'll talk about seismic India, but it's precisely about the Himalayas that I'm going to kind of concentrate on. Then I'll talk about earthquake weather, because whenever we talk about earthquakes, everyone wants to know, can you predict an earthquake? What do you do if there is an earthquake? And so on and so forth. So that's what I'm going to quickly touch upon, and then I'll tell you what my views are about making the society safe from these kind of earthquakes. So I'll start with this plot where you have deaths from earthquakes on the y-axis, and on the x-axis are the size of earthquakes. I'm sorry, it's kind of cut off. But what you can clearly see the moment you see this kind of a plot is for the bigger earthquakes, which are kind of on this side of the scale, you always have a larger number of deaths from these kind of big earthquakes. If I take a subset of this and look at some of the earthquakes that we have had in India, you can clearly see the same picture. But if I take another subset of this, and if I arrange them in terms of time, taking the oldest one first and the youngest one below, you can also see that the total number of deaths that you have for similar sized earthquakes actually have become bigger and bigger over time, which tells you that it's also a function of population density. And this is why we need to worry about earthquakes. So obviously the question that everyone asks and we answer over a long period of time is that, do earthquakes kill people? It doesn't. It's essentially the structures that we build which kills us. And therefore we need to think about it. So here is a plot that I've taken from Roger Willam, which actually shows you all the earthquake-prone zones in that pink band. And on top of that, what you have are two things. One is the number of deaths per earthquake, which is plotted as a yellow circle, and scaled by the number of deaths, which you have below here. And also on top of that, you have these black squares, which tells you the size of cities which are there across this region. And the moment you see a map like this, you clearly see that there are a large number of deaths from earthquakes in the past. So the bottom actually is cutting off. But what I'm showing you here are a histogram of the number of deaths from earthquakes from within India, which is within this part of the Himalayas, which is India, Nepal, Bhutan, all of this put together along the Himalayas. And you will see that there is 1 million people killed over the last century from big earthquakes. And the important message on this kind of a plot is that we are not alone. It's not just one country. It's everyone along the Alpine Himalayan belt who are getting affected. Now, if I look at our neighbor Iran, sorry again, at the bottom is cut, that's Iran, and you will see that the capital city of Iran, Tehran, has been destroyed in earthquakes again and again and again. So these are all the dates over which it has been destroyed. Similarly, if you look at the other places, you look at Almaty, Kazakhstan, repeated earthquakes which have destroyed the city. Look at Kathmandu, destroyed over several earthquakes. The same with Tashkent, Bishkek, Ashgabat, and all of these places. So obviously, this entire Alpine Himalayan belt is prone to big earthquakes. We know that. There are big earthquakes which kill a lot of people, and what is alarming is that a large number of big cities are very close to these earthquake-prone belts. So to take you closer to one of the big earthquakes that we had in the near past, this is a photo from a region in Muzaffarabad for the 2005 Kashmir earthquake. Look at this tree which I have circled in the front, and look at that township behind. This was before the earthquake, this is after the earthquake. Absolute destruction. This tree is still in the foreground. So this is what we are facing. This is what happens when you have big earthquakes. It actually destroys big towns and cities. And this is what we need to worry about. So obviously, as a society, we need to wake up to this danger. We all understand that there is a danger. Now the question is, how do we deal with it? So now I'll take a step backward and tell you why we have these earthquakes. So I'm going to give you a glimpse of what would be an first course in earth sciences, or plate tectonics as we call it, right? So after having looked at these kind of cities and the destructions over several earthquakes, one of the things that we always ask ourselves, are we really concentrating in the wrong places or in the most dangerous places? We are. And there is a reason as to why we are, because obviously all the rivers are there, all the fertile soil is there, and that is actually being built by the geology. And the geology is the cause of all these earthquakes. So let us try and look at the bigger picture of this geological phenomena which we call as plate tectonics. So here is a map of the globe. You have elevation and bathymetry. On top of this, what I'm going to do is I'll plot all the earthquakes as red dots. Okay, so every dot is an earthquake over the last 50 years. And what you clearly see that they are not everywhere. They are in specific regions around the globe, particularly in the oceans, and in the continents they are slightly widespread. And let's try and ask this question as to what are they defining? What are these dots defining? What these dots define is what we call as plate boundaries. But when I say plate boundaries, the obvious question is, what are these plates or plate boundaries? So let me take you on a journey which, if you have read this book as a child I had, which is Journey to the Center of the Earth by Jules Verne, where he talks about how you actually go to the center of the Earth through a conduit of a volcano. That's not possible, but obviously through geophysical techniques nowadays, we can look inside the Earth, we can probe by secondary methods. And what we now understand is obviously the Earth is holding primordial heat at the center, and that heat is escaping as a function of time, which means that the Earth is cooling, and there are two ways in which it cools. One is by convection, and the other one is by conduction. The deeper part of the Earth actually cools by convection, and the shallower part cools by convection. Now, if I take a closer look at the top part, and here what you see is depth on your y-axis and temperature on the x-axis, and what you see as this curve, which comes down, is basically telling you what the temperature is at different depths. And you can clearly see that there is this linear part of this curve, which is the conducting part of the geotherm, and then there is a deeper part where you are mixing or convection. So the part which is conducting heat close to the surface is what we call as our plates. So there is a fancy term that geologists use, which is called the lithosphere, but it's the same thing, right? So if I show you across continents and oceans in a cartoon, this is what it will look like. So the plate, or the outer layer of the Earth, which is cold, strong, can produce earthquakes, and is losing heat by conduction, is the plate. That's about 100 kilometers thick underneath the oceans. Now that is the layer which surrounds the Earth. So our Earth is divided into these plates. So we are a part of this Indian plate that you see here. So there are all these mosaic of plates which you have on the surface of the Earth. Now the next question obviously is, why should the earthquakes actually be along the boundaries of these plates, right? In the oceans, they are clearly defining all these boundaries, on the continents they don't, and that's a different story altogether. But let's look at why they actually define these plate boundaries. The reason is that these plates are actually in motion, constant motion. So the surface of the Earth is always shifting, slowly, but always. So we have a dynamic planet, and that is something which we understand. And this large-scale motion of these plates is what we call as plate tectonics. Now, the next question that you obviously ask is this motion two-dimensional? Does it only happen on the surface? Or is it three-dimensional? Does it go to depth? It does go to depth. So if you take a perspective view of it, this is what it does. So there are places where your plates are being created in the middle of the ocean, and there are places where they are being destroyed. So now I'm going to use a few movies to demonstrate as to how this process happens. So let's start with the creation part of it. I hope this works. Yeah. Sure. So this is where new plates are being formed. This is a movie from Africa where the Red Sea is splitting. You can really see how it's actually going to go apart and produce new plates. And the time that you see is in millions of years. So this is how you are actually producing new plates on the surface of the Earth. And as this moves away, every time there is an earthquake on that ridge. Now let's look at the region where you are actually destroying these plates. Yeah. So this is where you are actually taking plates away, and this is a region from South America, the Andes, and the Pacific Ocean on your left. So that's where you are actually destroying the ocean underneath the continent. And here also, as that part of the ocean goes down the continent, every time it moves in an earthquake, and that's what you see as shocks at that boundary. And then, if you continue to do this process with a continent riding behind it, then these two continents will come together and they will collide. And when they do that, what they do is they build mountains. And this is an example from the Himalayas as to how you build these mountains. So here you are looking at India colliding with Eurasia. So what you'll do is it'll basically take a step backwards and then it'll show you how it moves forward. So as you close the ocean in between, you will see India coming and colliding with Eurasia. So you move backward, and now you kind of push India forward. You close that ocean in between, which used to be called the Tethys Ocean, and you make the two continents collide, and what you have are earthquakes. Now here, you can see that the distribution of this region over which the deformation happens. So it's not just on a line, it's actually across a big region. And that is how the Himalayas form. So now if you take a step backward, this is about 300 million years, and sorry, it's kind of cut at the bottom. India obviously was not where we see it today. It was somewhere in the southern hemisphere and with all the other continents, and this was called the Gondwana land. The name actually comes from a tribe in the middle of India in Madhya Pradesh called the Gonds. So once India started moving northward, I'm going to show you the journey that India took. So here you see India in the southern hemisphere, you see all of that stuff on top. The number that you see on top is in millions of years, and this is what India did. India actually went northward and collided. And this collision is what raised the Himalayas. And this is what you see. If you went to the field, this is in Ladakh. This is a field we went to several times last in 2023. And you can clearly see this marker of India and Tibet together. So what you see here is India on one side, Tibet on the other side, and in the middle, the river is where the join is. That is where the two continents join. So that is known as the Indus-Sangpo-Sucha zone, which runs all the way from the west to the east. Now, if I put that on the map, the reason why you have all these earthquakes, which are each of these red dots, is basically because of India colliding with Eurasia. And as I said, that collision is not limited like in the oceans on a line, it's actually across this entire region. The moment you see an image like this, one of the things that you realize is that India has very few earthquakes, whereas Tibet has a huge bunch of earthquakes, which tells you that there's a contrast in the strength of the material across these two regions. All of Tibet is crushing up, India is kind of plowing into Tibet, and you have all these earthquakes. So each dot is an earthquake. Now what I'm going to do is I'm going to take a closer look at these earthquakes to one of these dots, or in other words, I'm going to show you how you cause an earthquake. Here what I'm showing you is an earthquake from California, and you can see that there is a river which is flowing down like that. It comes and stops and then continues on the other side. And what you see is that the river is offset along that red line, and that's your earthquake fault. So that is the fault which moved by 8 meters. So the top moved by 8 meters in that direction in one big earthquake. And let me use a small cartoon to show you this. So again, I've plotted the same thing here. The red line is the fault on which earthquakes happen. The top will move to the right, the bottom will move to the left, and you will see how the strain in the material builds up, which means how you're squeezing the material to produce these kind of earthquakes. So the brighter the color is, the more it's squeezed. So you see these two are moving in two directions. This happens over years, and then finally when the material cannot hold anymore, it breaks. Only a part of it breaks and it produces that fault, that's the red line. So that's the earthquake. It happens in split seconds, and where it starts is what we call as hypocenter, and then it kind of propagates in one direction. Again, to show you that's what happened. So you see it's straining the material and then breaks in earthquakes. And that is what India is doing. India is slowly pushing into Tibet and it's creating all that strain which produces all these earthquakes. Now you can see that in the field, the same earthquake that I showed you before in a different location, that's what you see. You can clearly see that the beds are offset, the markers are offset, and you get this big fault which runs through the middle. Now let's come to the Himalayas and see where this big fault is. Now, as you all understand, Himalayas or India, Bhutan, Nepal, we are all surrounded by all these big earthquakes that happened in the past. These numbers basically tell you the year when these earthquakes happen. If you take a closer look at the Himalayas, what you are seeing here are three things. One is, the bottom is India, the top is Tibet. The numbers that you see in blue are in millimeters per year, and the arrows actually tell you in an India fixed reference frame. So if I hold down India, how is all of this moving towards India? In millimeters per year, it's about 20 millimeters per year. That is the reason why you produce this strain in the middle. And what you see on top of this are these ovals, which are basically the rupture zones of the past big earthquakes. The numbers that you see within those ovals around them are the year in which these earthquakes happened, and you can clearly see that the whole of this zone is marked by big earthquakes. The third thing that you see on here are the text in blue, which tells you that there are some regions in the Himalayas where there hasn't been a big earthquake in the last 500 years or so. And these we term as seismic gap. It's actually not a gap in the seismicity, it's just that it's straining elastically and will produce an earthquake in the future. It hasn't happened in the last 500 years, which means that these are regions which are in a position to produce a big earthquake. And how do we say this? I'll come to it. So if I look at this, so that's the direction in which India is pushing into Tibet, or if you put India down, that's how Tibet is moving towards India, and that's why you have these earthquakes. Where is the big fault? The big fault is at the front. The red line precisely marks the region where you are actually going to have an initiation of the big earthquakes, which is essentially the region where India goes down. If I take a block model across that region, this is what it will look like. So what you're seeing is, on your left is India, on your right is Nepal. It can be Nepal, it can be Bhutan, it can be Kashmir. So that's the region that you're looking at. And what you're seeing is India going in the underbelly of the Himalayas, and it's happening along that direction like that. The line, the black line, is basically the fault which goes at depth. That is the one which facilitates the motion of India underneath the Himalayas, and the shallow part of that fault is locked. The reason why it's locked is because it's cold and frictionally locked. The deeper part is sliding freely, and the region which is locked is the region which produces these earthquakes. I'm going to show you this thing in a movie, which is here, as to how this happens. So here what you'll see is India moving down in the underbelly. See that shallow part is locked, and then you start, once it overcomes the frictional locking, it produces these small earthquakes, and then the big one. I'll play this out again. Just look at that region where you have the red locked part. So this is pushing down, that's pushing over. You have the smaller earthquakes, the 6 magnitude kind of earthquakes, and then you have the big one which pushes the whole thing out. And this is the cycle which repeats again and again and again, and you have these big earthquakes. Yeah, so these are the big earthquakes, and obviously all of India is going in the underbelly of the Himalayas. Now, obviously these are the earthquakes that I was referring to. The one that happened recently was the 2015 earthquake, and that's the one which is in Nepal, in eastern part of Nepal. And I'm going to tell you what the technology now allows us to do. We can actually see how this earthquake happens second by second after it has happened by using the data that we acquired. So here is a study that we have done. So what I'm showing you is that region of Nepal. I'll blow it up and I'll show you second by second how the earthquake rupture propagates. So you can see it started in the west, and that front, that red patch is where 90% of the energy is coming out, and it goes from west to the east. So you can see the fault breaking at depth, which goes like that. So that's what we can do nowadays. We can see exactly how the rupture happened. And once this happens, obviously it causes a lot of destruction. So this is the Kathmandu Valley. What we are looking at the mountains at the back, and you can see the build-up area of Kathmandu. Once this earthquake happened, the next thing that we understood is that not all the ground underneath your feet shakes the same way. And that is what I'm going to demonstrate by using 2 points, one on the mountains, one within the valley. The blue dot is on the mountains, the orange dot is on the valley, and you will see how these 2 dots will move when the earthquake happens. Notice they have permanent motion, and then notice what the orange dot does. So this is in real time from GPS. So you see the 2 regions are actually responding differently to the earthquake. So you can see that the blue one went there and stopped. The orange one actually wobbles like jelly because it's sitting on mud, it's sitting on sediments within the valley, and that is what it does. It's kind of going on. And that is one of the reasons why you had this differential destruction. So if you look at the same region, look at all the destruction within the valley, look at the buildings back in the mountains, they are less destroyed than the ones in the front. And this is something which we need to be aware of. When you have an earthquake, everywhere it's not going to hit the same way. It's actually dependent on what structure you build, on what material, as to how your buildings will respond. Now let's move forward. Once I've told you all of this, the obvious question everyone asks is there something called earthquake weather, or can we predict earthquakes? So obviously the answer is no. We cannot predict earthquakes. But that's not a one-shot answer. There is more to it. First, let me tell you the reason as to why we cannot predict earthquakes. We understand the material properties of the earth. Imagine it's like a layer cake. There are a lot of engineers in the room, and obviously it's an engineering problem. If you apply stresses at the edges, you can predict the failure of these kind of structures if you know what the structure is, right? So in other words, if you ever had a crack on the windscreen of your car, you know that the cracks have maximum stresses at the points where it stops, and therefore those cracks are actually going to grow in that direction. And you can actually calculate what the stresses are, you know how it moves. But the problem with the earth is that it's absolutely smashed up. So we have a really old material that we are dealing with. It's not like just one crack propagating in a particular direction. So we have a 4.2 billion year old earth, which means that it's all smashed up with all these faults. A lot of them we know nothing about. And therefore it's not straightforward to predict earthquakes or predict their failure. It's not a standard engineering solution that you can apply to predict these kind of earthquakes. So obviously if you can't, then are earthquakes unpredictable? This question is a bit nuanced. There are 3 things when you talk about prediction. The first is, where is the big earthquake going to happen? The second is, how big is it going to be? And the third is when, in terms of exactly when. So obviously using all the signs, we can tell you where and how big. And that is what we call as long-term forecasting. And this is based on scientific evidence. And therefore we can tell you that. What we cannot tell you is when. And let me give you a bit more insight into this. So this when is the short-term prediction, and this should not be linked to public safety, and I'll tell you why. So first, let me address that question of where. With all the science that we have done, we now understand that the Himalayas, or the plate boundaries which you have along the Java-Sumatra subduction zone, are the regions where you are going to have these big earthquakes. So obviously we know where the big earthquakes were, and we know where the big faults are, how they are being sprained, and therefore we know where these earthquakes are going to be. The second question is how big. This is a figure that I've taken from Roger Willem. There is a clear understanding by looking at all the past earthquakes and from the convergence that's going on as to how big an earthquake do you expect in the Himalayas. And the difficult part is that there is an 8 magnitude earthquake almost poised to happen everywhere. Now when I say 8 magnitude, what do these numbers mean? Because it doesn't really mean much to a person who doesn't deal with earthquakes. To give you a simple example, here is a plot, ignore all the details. What I've got on the y-axis there are the magnitudes of earthquakes, and look at this little dot here, the Hiroshima atomic bomb. So let me reference it to that. That's close to a 6 magnitude earthquake. What we are dealing with is an 8 magnitude. So if it's 7, it's 32 times more energy that you are releasing. If it's 8, it's 1,000 times more energy that you are releasing. So that's the magnitude that you're looking at. If it's 9, it's 32,000 times more energy compared to that Hiroshima atomic bomb. So that is the size of earthquakes that we have to deal with. So that is how big it's going to be. Now, the third part was when. And as I said, that is something which we cannot tell you, or in other words, we cannot tell you tomorrow 8 o'clock there will be an earthquake. And even if I did, this is going to be dangerous. Because if you link this to this short-term earthquake prediction to public safety, you are actually going to kill people. And there are multiple examples, I'll just give you 2. One is the L'Aquila earthquake in Italy, which happened in 2009. There were only 300 people killed, but the problem was that an administrator, along with 5 scientists, actually assured the people of L'Aquila that there won't be an earthquake tonight. You can go back home and sleep in peace. They did, the earthquake happened, and people were killed. And they all understood what earthquakes were, they all understood the risk from earthquakes. The reason they took these people to trial is because they said something which was not based on scientific evidence. Obviously, they were sent to jail. Later acquitted, but the administrator was not acquitted because it was his responsibility. The same thing happened in China. China somehow thought that they had predicted an earthquake which was of 6 magnitude before the Phuentsholing earthquake. And they thought that they had solved the problem. The Phuentsholing earthquake happened within months of it, killed 83,000 people. So short-term prediction does not really help you. So you obviously need to use the science to make society safe. And here is my view on this. So what I think is the way forward is to have a synergy, and that's the reason why we are having this kind of a workshop. A synergy between scientists, engineers, architects, planners, civic leaders, educators, and public. It's a 3-way traffic. So we need to come together to ask a few very simple questions. The first, as a scientist, we need to ask this question: what is the hazard? With all the scientific knowledge, we should be able to answer that. The second is, the moment you understand what the hazard is, you need to ask the engineers, can you deal with this? And engineers are smart people, a lot of them in this room, they know exactly how to build buildings which will not fall. And therefore, they need to use the scientific knowledge to make buildings safe. And then we need to turn to civic leaders, educators, public, and this communication has to be set up by social scientists, because we can't speak the language that the public will understand. And most of the time, if scientists do that, they actually miscommunicate. So there has to be a tie-up among all of these, and we need to ask this question: are you going to prioritize risk reduction? Here I just make a quick point. Hazard is what the earth does to us. We cannot control it. What we do to ourselves is what we call as vulnerability. If you build a building which is poor quality, it is vulnerable. So you multiply, think of vulnerability as a number on a scale of 0 to 1. If your vulnerability is 0, you multiply it with hazard, produces risk, which is 0. Whereas if you have a poor building, high vulnerability, you translate the hazard to risk. And that is what we need to control. And this is how we move forward. So in summary, and I'm going to give you one example of how this has been achieved. And this is a big success story from Nepal. Here is Amol Dixit, who runs this place, which is known as the NSET, which is the National Society for Earthquake Technology. We visited NSET as a part of the Earthquake Without Frontiers project back in 2015, a week before the earthquake, and we saw the kind of work that they had done. It was phenomenal at the ground level. I'll give you one example of this. You know, this earthquake actually destroyed a very large number of houses and also destroyed a very large number of schools. There were almost 80% of the schools which were exposed to these earthquakes, which were destroyed. However, not all of them. What NSET had done is, in villages, they had actually taken up government schools and they had retrofitted them. That's the old school, this is the retrofitted new school. If you look at it from inside, what they did was they put in beams and columns within the walls of these old buildings, plastered them, painted them up, and these were how the classrooms looked. They were perfectly usable, they were very nice buildings, and these were retrofitted to actually withstand this earthquake. 323 of these schools were retrofitted, and all of them survived this earthquake. It was a really remarkable story. And I can tell you more about these. So this is, I think, the way forward. If we actually use science to make our society safer, this is how we can survive from future hazards. So here in summary, what I told you is we live on a dynamic planet. We can't control how it manifests itself. It does in terms of plate tectonics, produces earthquakes, which are a consequence of these plate tectonics. What we need to do is we need to use our scientific understanding to quantify hazard and then join hands to mitigate what the risk is. And this is what we do at IISER-Kolkata at the Seismological Observatory. Thank you very much for your attention. So do I take questions? Or? Okay.
Maybe one or two questions while you are here.
Supriyo, I have a small query. That we are saying the plates are going to shift it.
Yeah.
How it is measured? Somewhere it is telling that 20 mm.
Yeah.
Measuring 20 mm of that particular big slot.
This is exactly what the triumph of GPS is. See, we use both kinematic and differential GPS, which actually gives us millimeter scale measurements on the horizontals. On the vertical, it's poor, but we can do that. So, to a millimeter, you can actually use multiple GPS stations to tell you exactly how 2 points are moving with respect to each other. Okay, and the uncertainties of these numbers are less than a millimeter. That's how.
By using GPS only.
Yes, absolutely. Yes, by using GPS. So what you do is you put all these GPS stations